Hello students, in this video we will be learning about the pulse code modulation. Pulse code modulation means PCM in the short form. Very important for gated ESA examinations. The questions from the digital communication means the question from the PCM. There is no question paper without having the problem in PCM. Now I will explain the block diagram of PCM. What is the first block we are having in PCM? The first block is, students, low pass filter. This low pass filter also called as anti-aliasing filter. Low pass filter or anti-aliasing filter. What is the work of this low pass filter or anti-aliasing filter, sir? In the review of Fourier transform topic, I given that if you take a small rectangular pulse of width t or tb, if you calculate the Fourier transform for that, you will get a bandwidth of infinite. But important frequencies are up to certain value only. Means we need to limit up to there. The meaning is, general practical messages are having frequencies up to very large, but the significant components are only up to a specified value. So we need to send those only. Are you understand my point? Like in the voice signal, having frequencies up to 7-8K also, but important components are only up to 3.4. So we are limiting up to there. How we are limiting? By taking the low pass filter, cutoff frequency is equal to the last significant frequency component in the message. There, if you see the review of Fourier transform, for that rectangular pulse we got the bandwidth infinity, but by filtering out we got the bandwidth is 1 by TB. So the first block, not only here, I told number of times, the first block in communication system will be low pass filter to band limit the messages. Why I am also calling anti-aliasing filter? Because if it is having infinite frequencies, I have to maintain sampling rate to fs equal to 2 into infinity, means infinite I have to maintain. If you are unable to maintain infinite, aliasing problem. But it is preventing that. So anti-aliasing filter also. For example, this low pass filter having cutoff frequency FM, means it allows all the frequency components up to FM. Got my point or not? So the first filter, that is, the first block, that is low pass filter, LPF means low pass filter, will band limit the message. What is the next block, sir? What is the next block in PCM? The next block in the PCM is nothing but the sampler. The sampler. What is the work of the sampler, sir? Sampler will convert the continuous time signal into discrete time signal without any information loss, provided that the sampling rate Fs is greater than or equal to 2 FM samples per second. Practically greater than only, oversampling is preferred. For example, output of the sampler, let's call some M of NTS, because the samples are coming at some regular intervals of TS. That is 1 TS, 2 TS, 3 TS, 4 TS, 5 TS, 6 TS, like that. The discrete time signal is the integer values on time axis. Suppose if I draw the graph between M of NTS versus NTS, what is the output of the sampler? A simple logic, simple thing. Sampler output is nothing but the amplitude of the message signal at some regular intervals of TS. That is nothing but 1 TS, 2 TS, 3 TS, 4 TS. At these instants, what is the m of t? Amplitude. The amplitude of a m of t at nts. At nts. So, for example, the sample value at t equal to ts is some random values I am writing. So these are not standard. For example, if this value is 0.9, at 2ts, for example, some 1.6. At 3ts, for example, some 2.7. At 4ts, for example, some 3.8, like and so on. Means, what is the sampler is giving, sir? Sampler is giving the amplitude of a message signal at ts, 2ts, 3ts, 4ts, and so on. It is collecting those samples. From those samples, you can get the original continuous time signal back. If you are providing at least fs is greater than or equal to 2 fm, where fm is the bandwidth of the given signal or highest frequency of that. Clear? Yeah. After the sampler, what is the next block we are having, sir? The next block we are having is in the PCM Quantizer. Very, very, very important. What is that block, sir? Quantizer. First, let's see what is a quantizer. Each and every quantizer will have, or the quantizer will have some fixed number of voltage levels. Quantizer will have some fixed number of voltage levels, also called quantization levels. Generally, number of quantization levels are denoted with L. In old-fashioned books, they are also written with the capital A, but now in the recent books, generally number of quantization levels are represented with L. Now, for example, in this situation, L value, let me take 4, for example. So, those 4 quantization levels are, for example, 1 volt, 2 volt, 3 volt, 4 volt, for example. How to set those we'll discuss, wait. But here, for example, I taken. What is the quantization process? We'll see, wait. So, let's take the output of the quantizer is, students, some MQ of NTS. So, I am drawing the graph between MQ of NTS. I am drawing the graph between MQ of NTS versus NTS. What is the work of the quantizer, sir? What is the work of the quantizer? Quantizer will round off each and every sample value to nearest quantization level. Try to understand. Quantizer work is to round off to nearest quantization level, not to the nearest integer. Try to understand. Quantization levels may be non-integers also. The work of the quantizer is, it will round off each and every sample value to nearest quantization level. So, 0.9 is nearer to which quantization level? S1. So, it is rounding off to 1 volt. 1.6 is nearer to 2. So, it is rounding off to 2. 2.7 is nearer to 3. So, it is rounding off to 3. 3.8 is nearer to 4. So, it is rounding off to 4. Are you getting? Why we have to doing like that? We will understand, wait. These are the actual samples, but why we are making like that? You will understand in the last. But here, try to see the forward operation. What is the quantizer is doing? Quantizer is rounding off each and every sample value to a nearest quantization level. Clear? Yeah. After the quantizer, what is the next block we are having is, students, the next block is, the next block is encoder. Actually, quantizer and encoder will be on a same circuit itself, but as a block diagram I am writing separately. encoder. Sir, what is the encoder, sir? Encoder will generate a unique binary code. Encoder will generate a unique binary code for each and every quantization level. In this example, how many possible inputs received by the encoder? In this example, 4. Because the number of quantization levels are 4. The number of inputs received by the encoder is nothing but the number of quantization levels. Are you getting my point? So that is, L is also equal to 2 power n. In this example, I can say n is 2, where n is called, students, number of bits per sample. Where n is called number of bits per sample. Here L value is 4, so n is 2. So to get the 4 different binary codes, you can think also. To get 4 binary unique codes, your unique binary codes, how many bits are received? 2 bits. Oh, sorry, how many bits are needed? 2 bits are needed. What are the codes? 0, 0, 0, 1, 1, 0, 1, 1. Got my point? For example, L value is 8. 3 bits are needed. 2 per 3 is 8. So the work of encoder is, student, it will generate a unique binary code for each and every quantized sample. Each and every quantized sample. Now see, encoder output is nothing but, student, the PCM signal. Now, what is the first one received? There is an internal mapping between the quantizer and encoder in such a manner that 1 volt came, send 0, 0, 2 volt came, 0, 1, 3 volt came, 1, 0, like 4 volt came, 1, 1, like there is a unique mapping will be there. In the decoder side, I have to get back the original message also one more time. So there is a 1-to-1 mapping will be there between the quantization levels and the encoding symbol. So, what the first one came? 0, 0, sorry. First one came is 1. 1 means, what is the code you will get? It will generate 0, 0, next 2, 0, 1, next 3, 1, 0, next 4, 1, 1. Like the codes will be generated. The generated codes we can transmit only through cable because it's a low frequency one. You cannot transmit through free space. So PCM, DPCM, delta modulation, adaptive delta modulation, these all output of the transmitter will transmit only through cable. If you see the name of the topic is Pulse Code Modulation. Yeah. Can you please help me in answering this problem, in this question? In the Pulse Code Modulation, where is the modulation going on? Can you please help me? In Pulse Code Modulation, where is the modulation is going on? Yeah, someone is saying quantizer, okay. Someone is saying sampler, right? Someone is saying encoder, okay. Try to see what is the meaning of a modulation. The meaning of modulation is changing the carrier parameters. Where is the carrier I taken there? No. No carrier means no modulation. The meaning you need to understand, in pulse code modulation, no modulation is going on. If you clearly see, the input is a continuous time signal. The PCM output is nothing but a digital. So, PCM is a technique of conversion of continuous time signal into digital signal. PCM, DPCM, delta modulation, adaptive delta modulation, all these 4 techniques are meant for conversion of continuous time signal into digital. This digital signal, if you want to radiate to free space, you need to go for modulation. Those are nothing but ASK, FSK, PSK and MRA schemes. So that's why here I told the generated signal we can transmit only through. Now, here we got the zeros and ones. What is meant for 1, what is meant for 0? Here for representing of this, we are having different signaling schemes. Of course, what we are using in PCM is, students, NRZ technique, sir. What is NRZ? Non-return to 0. What is non-return to 0 means, in this technique, 1 is represented by a positive pulse, 0 is represented by a negative pulse. Both are of same duration, TB. About the TB formulas also will get calculated. B means do bit. B means bit. Bit duration, TB. So you can see there. Zeros with the negative pulses. Ones 1 with the positive pulses. Zeros with the negative. Like fixed duration will maintain, don't bother about that. With the positive, like it will be there. Means the generated PCM signal is what we generated here, 0 0 0 1 1 0 1 1. The generated PCM signal we can transmit only through the cable. Now follow. Any signal is transmitting through the channel, noise is going to be adding. Noise is an unwanted signal which is disturbing our wanted signal. So in the channel, what is going to be adding? Noise. After adding the noise, the same signal will becoming like this. Still if I extend, still more noise will be adding. So our information is corrupted. By up to here, yes, noise is added, still I can able to recognize what are zeros and what are ones. But still if we extend, student, the total information is going to be corrupted. But here in digital communication, in the PCM, we are having one excellent thing, sir. We are having one excellent block, sir. That excellent block is nothing but regenerative repeater. What is that excellent block is called, sir? Regenerative repeater. Regenerative repeater is nothing but one comparator circuit having some specified threshold level VTH. Whenever input received by RR is greater than VTH, it will generate one symbol. Whenever input received by RR less than threshold, it will generate a 0 symbol. Are you getting my point? Input greater than threshold, 1. Less than threshold, 0. Equal to threshold, undetermined. Ambiguity will get. So, what is the RR work keys? It's the most important block. Let me write the first RR output and then I will get back. So, coming to the RR output, see, this is a nice one is came. And how we are setting that threshold values are? Threshold is actually we are setting, it's an average of how much voltage we are sending for 1, how much voltage we are sending for 0. That average will take generally to get better probability of errors. For example, for 1 I am sending +5, my 0 I am sending -5. Then what is the average, sir? Average is nothing but plus minus 5 average 0. So threshold will keep as a 0. Are you getting my point or not? The threshold is 0. Now see. Yes, our PCM signal came. Noise added. Even though here it's looking like less than 0 or greater than 0. Less than 0. Input less than threshold. So 0. Next input less than threshold. Input less than threshold. Input greater than threshold. Greater than threshold. Less than threshold. Greater than. Means the regenerative repeater will freshly regenerate the PCM signal exactly back by deleting the total noise adding in the channel. So that's why this PCM is totally eliminated from the channel noise. It doesn't have any effect of channel noise. If it does not any effect of channel noise, then you can use it for a long distance communication. So when compared to analog digital communication, of course PCM is preferred for long distance communication because there is no channel noise, because it is completely eliminated by the regenerative repeaters. Like we are placing regenerative repeaters in such a manner that it completely reduces the channel noise. How many regenerative repeaters we have to place is mainly depending upon distance between the transmitter and receiver as well as quality of the cable. If the quality of the cable is good, less noise will be added. Cable quality is not good, obviously more noise. Just like I can take a simple example. For a suppose you are listening the songs from your mobile phone by using headphones. You are having two sets of headphones. One you purchased from the branded Sony showroom, another you purchased from the roadside in Koti. Koti means it's a place in Hyderabad. Are you getting my point? Now you can see the difference. The difference is nothing but a amount of adding noise. Still there are a quality receivers also there, or quality headphones also there in thousands of rupees. You can listen the songs in those, still you will get a more clarity of that. Are you getting my point or not? Yeah. So finally, the number of regenerative repeaters are depending upon distance and quality of the cable. Because of them, digital communication is free from channel noise. So that's why you can use it for longer distance communication. Like regenerative repeaters we are placing, coming to the receiver side. What is the last block in the transmitter? Encoder. Opposite operation of an encoder, that is nothing but students, decoder. What is the decoder will do, sir? Can I write here decoder output? If I write the decoder output diagram, the decoder is nothing but exactly opposite to encoder. So here, if you give 1 volt, encoder will give 0 0. Now 0 0 giving to encoder, then 0 0 giving to decoder, it will generate 1 volt. This will maintain exact duration of TS. That we will maintain, don't bother. Next, 0 1. 0 1 means 2 volt. Next 1 0, 3 volt. Exactly inverse mapping. 3 4 like and so on. There is a 1-to-1 unique mapping I already told. So corresponding voltages will be reproduced. These quantization levels may not be integers also, I told. For starting example I taken like that. You can see in one gate problem also 1.5 is the quantization level. Yeah. So decoder will do the inverse operation. Next. Quantizer. Yeah. Can you please tell me what is the inverse system for quantizer? What is the inverse system for quantizer? Dequantizer, okay. Sample hold circuit, okay. Any other? For a quantization, no inverse system, sir. For a quantization, no inverse system. Why? I will explain you, wait. So, before that, what is that sampler? For sampler, inverse system is low pass filter. Then it will reconstruct our M of t back. But I can say MQ of t. Why? Because for the quantization, no inverse system is there. So permanently in the reconstructed signal, there exists a small amount of quantization noise. We'll try to maintain that value as small as possible. Then we can reconstruct our signal back. So what is the low pass filter will do, sir? I am writing the low pass filter output with the red colored one in the same block. What is the low pass filter will do? Low pass filter will charge to all the samples. is charging to all the samples means it will reconstruct the original message signal back. Are you understand my logic or not? This is the overall operation of a pulse code modulation. So here the point you need to understand, sir. One is quantization is irreversible. Why quantization is irreversible, sir? See, for example, this quantizer, if I give 0.9, 1 volt, 0.91, also 1, 0.92, also 1, means for different inputs, quantizer output is the same. The system is producing same input for different, same output for different inputs. In such type of case, we are unable to provide inverse system. We are unable to provide inverse system means the given system is irreversible. In the classification of systems, in the classification of systems, invertible and non-invertible systems. Electrical systems generally becomes non-invertible in two cases. First case, producing different outputs for same input. Producing same output for different inputs. Producing zero output for non-zero input. In these two cases, not. Here the system is producing same output for different inputs. It means if I design the inverse of the quantizer, it takes one, but it has to produce different outputs. How the system will know whether to produce 0.9 or 91 or at 92? Because whatever may be the value here, it is receiving the same input. Are you getting my point or not? So that's why quantization is irreversible. Because of that, some quantization noise will be there. We'll try to maintain that value as low as possible. This is the overall operation of the pulse code modulation. Here I given only one RR, like number of RRs will be placed, sir. Clear?